We've just seen two really important linear algebra definitions. The first being that we defined a sequence of vectors to be linearly independent if and only if the only linear combination which gave you the zero vector was the linear combination where all the scalars were zero. And the second being that of a spanning sequence. So a sequence of vectors was a spanning sequence if and only if you could write every vector in the vector space as a linear combination of the vectors in your sequence. Sequences which have both of those properties at the same time are particularly interesting and useful to us, and they have a special name which is a basis. So here's the definition of a basis of a vector space. A basis is a sequence of elements which is linearly independent and a spanning sequence at the same time. So let's jump straight in with an example of this, and then I'm going to highlight an important property of the definition once we've done that. So the first example is we take our vector space to be R squared, and we take the two elements. Let's call this E1 is going to be 1, 0, and E2, 0, 1. Those things are a basis of the vector space R squared. We've proved in the previous couple of videos that those things are linearly independent and they are a spanning sequence, and so they're a basis of R squared. And to take another example, if we take U1 to be equal to the vector 1, 1, and U2 to be the vector 1, minus 1, then again we have checked that this thing is a spanning sequence. Remember, we had to solve some linear equations to check that, and we've also checked that those things are linearly independent. So these are a different basis of R squared. So already there's an important observation. The same vector space can have lots of different bases. So here is an example of two different bases for R squared. Okay, let's take one third example just super quickly. If we let M2 by 2 of R be the set of all 2 by 2 real matrices, then I'm going to leave it to you to prove that the four matrices 1, 0, 0, 0 and 0, 1, 0, 0 and 0, 0, 1, 0 and 0, 0, 0, 1, those four elements of that vector space form a basis. Okay, so those are a few examples. Let's return to the thing which I wanted to highlight about this definition, which is the important thing here, a sequence of elements. Okay, not a set of elements, a sequence of elements. So what's the difference? Well, a sequence has the property that order matters. Right? In a set, order doesn't matter. The set 1, 2 is equal to the set 2, 1. For sequences, that's not the case. The order of a sequence matters. So that's the reason we're using sequences. It's because we want our bases to be ordered things. We want the order to be important. So we will consider E1, E2 to be a sequence of vectors. The order that you have them matters. You'll see why later when we start talking about matrices of linear maps. Okay, so let's look at a generic example of bases, which is the example of the standard basis. So if you give me any field f, so here f will be some field, any field. It might be the complex numbers, it might be the real numbers, it might be the finite field of order 5. Then we can form f to the n, which is the set of all column vectors of height n with entries coming from this field. So like r to the n, for example, is the set of all column vectors of height n with real number entries. And it's very easy to write down a particular basis of f to the n called the standard basis, and that standard basis consists of the vectors e1 up to en, where ei is the vector which has a 1 in position I and zeros everywhere else. So if we just take it as an example, n equals 3, then there would be 3 vectors in the standard basis. You would have e1 being this, E2 being this, and E3 being this. And those things are a basis for R cubed, or C cubed, or F cubed, where F is whatever field that we're thinking about. Those things form a basis for that vector space. And again, it's actually really easy to see why they're a basis. So if you want to check it, we have to do linear independence first. So let's just do the case n equals 3. You can find the general argument in the lecture notes as usual for this section. So if we want to do linear independence, well, if you have a linear combination A times E1 plus B times E2 plus C times E3, and that linear combination is the 0 vector, then just work out what you've got on the left hand side. A times E1 is the vector A0, 0, and B times E2 is the vector 0, B0, and C times E3 is 0, 0, C. So when you add those up, you get A, B, C, and the right hand side was 0, 0, 0. So A is 0, and B is 0, and C is 0. We've shown the only linear combination of E1, E2, E3 equal to the 0 vector is the linear combination where all the scalars were 0. That's the definition of linear independence. So we then have to do spanning. We have to show that E1, E2, E3 is a spanning sequence. So you have to take any vector, any element of F cubed, and show that it's equal to a linear combination of E1, E2, and E3. So just take anything, any vector x, y, z in F cubed. No matter what F is, it doesn't matter. Then this vector x, y, z is of course the same as x times E1 plus y times E2 plus z times E3. So every vector in F cubed is a linear combination of E1, E2, E3. In other words, the span of E1 and E2 and E3 contains every vector in F cubed, so it must be all of F cubed. Right, we've shown it's linearly independent, we've shown that it is a spanning sequence, and so it is a basis called the standard basis, and this is completely standard terminology, as the name suggests. You will find this used everywhere, and we will always we will refer to this several times, and we always mean this particular basis.